So today we're starting Unit 3. Unit 3 is physics. Okay? One of the most important concepts in all of physics is the idea of energy and the concept of mechanical energy especially. Okay? What is energy? The ability to do work. Okay? That's the strict definition of energy. All right, so when it snows, 30 centimeters, and your mom or dad comes and wakes you up, and says, go out there and shovel the snow, and you're like, I don't have any energy. You're full of crap. I mean, you obviously have energy. You're awake. Okay, but if you actually didn't have any energy, you would be completely incapable of shoveling the driveway. All right, because shoveling the driveway is work, and you have to have energy to do that. Okay, the reason you have to have energy to do work is because work is a transfer of mechanical energy. And you can't give away or transfer what you don't have. Okay? So the two ideas go hand in hand with each other. Okay? Energy is the ability to do work, and work is the transfer of energy. All right? So if I drag this desk, for example, okay, I've just done work. Do I have a little less energy than I had before? Yeah, I do. Because I gave it to the desk. Okay, I moved the desk. All right. It doesn't look like the desk has any energy now. It doesn't. Okay? But I had to pull it against the force of friction. It made a little bit of sound. Maybe it got a little bit hotter on the bottom or whatever. Okay. All of those are examples of different forms of energy. That's what my work was converted into. Okay, when I did that. Right. So to do one thing, you have to have the other. Now, what we're going to look at are, today, different types of energy. Okay, mechanical energy is probably the most important type, even though we won't talk about it very much today. It'll be the most important type that we do go over in this unit, because it involves the movement of objects. Okay, but we'll go over a bunch of different types, and we're going to look at conversions of energy from one kind to another. All right, those are really important because they're the kinds of things that make everything work. All right, just to be able to charge your phone, requires many energy conversions. Okay? In Alberta, we burn fossil fuels to make electricity. It used to be mostly coal. Now we're kind of shifting away from that more to natural gas. Okay? But we're still taking chemical energy in the fuel. We're burning it, releasing it as heat. Okay? And in most cases in Alberta, that heat is used to boil water, turn it into steam, and the steam turns a turbine. Okay? So there's a bunch of energy conversions that go on just to get the electricity that then gets to your phone and then is converted, through like magnetic fields and whatever into the stored chemical potential energy that's in the lithium-ion battery that powers your phone. Okay? So we actually go from chemical energy back to chemical energy, but we transfer it into a whole bunch of different kinds in between. How efficient is that? Not very. Okay, and in fact, the way we generate electricity in basically anywhere in the world is incredibly inefficient. The way we transport it is incredibly inefficient. Every time you transform energy from one type to another, you lose some, because no conversion of energy is 100% efficient. Okay? So if we're looking to improve efficiency and things like that, we have to look at the energy conversions that are involved, and if we can make any of them better or outright eliminate some of them. The more we can eliminate, the more efficient things are going to be. Okay? That's why everybody jumped on board the solar energy train. Okay? When it was really big there for a while. And it was like, well, we're converting it directly into electricity. And you're absolutely right. We are. Okay? When you use a solar panel, you're converting the sun's energy directly into electricity. There's no intermediate conversions like in a coal-fired or natural gas-fired power plant. Problem is, a coal-fired natural gas plant, a natural gas electric plant can last for a really long time. How long is a solar panel effective for? A few years at best. If you get 10 years out of a solar panel, it did pretty well, okay? But they do start to break down. The other problem with solar, at least around here, is when we need electricity the most is also when we have the least sunlight, okay? Like right now, we're heading into the darkness, Okay, soon it will be, you know, winter time. Well, it's going to be there again. Okay, but we're heading into that, you know, where we're going to have those 6 hours of sunlight, okay, days, and that sunlight is so low on the horizon that it basically does nothing. The sun makes this pathetic little arc across the southern sky, okay, and we can't really generate very much electricity, and of course that's when we need it the most. So solar energy is wonderful if you're in a place where you can have access to it and use it. Okay, it gets to be a cloudy day and you're dependent on it, you're kind of screwed. Okay, and the same is true for wind power. All those clean forms of energy are wonderful. The problem is they're not as consistent or reliable, okay, as, well, I got this tank of fuel, and as long as I got fuel in the tank, I can keep making power. Okay, that's a bit more reliable, or a pipeline is bringing it in, or whatever.
Nuclear energy.
Nuclear energy, also highly reliable. Okay, highly reliable and very safe, contrary to what a lot of people would tell you. There are very few nuclear accidents. The problem is when you do have one, it's somewhat catastrophic. Okay, you know, a coal-fired plant breaks down and you have a bit of a fire. Worst case scenario, there's a little bit of a fire, and that's really about it. Okay, there's no massive environmental damage or death generally. Okay, you know, whereas if you have a nuclear accident, that can be a problem. The other problem obviously with nuclear is the waste. While they don't produce a lot of waste, like by weight, what they do produce is pretty awful. Okay, like nuclear waste doesn't ever break down, or at least not in a practical sense ever break down. It's thousands of years. It has to be stored somewhere where its radioactive properties are not going to hurt anybody, which means specialized facilities, very deep in the right kind of rock, can't be porous, can't leak, okay, all of that kind of stuff, encased in concrete and forgotten about for thousands of years. Okay. So there's drawbacks to it. I mean, but when it's working, it's great. Okay? It's very reliable. You can change if you need more. You just crank it up. Okay? It's a great way to generate electricity, but it does produce pretty awful waste. Okay? And then that's not to say that a natural gas plant also it doesn't produce awful waste. It produces a lot of carbon dioxide, okay? Which is greenhouse gas. Okay, and so that could be a problem as well. What people won't tell you about some of the other stuff is like when a solar panel breaks down, what do you do with it? It's garbage. And it contains a lot of heavy metals and other pollutants that are not really good for the environment either. Okay, the same would be true, you know, if you buy an electric car. Okay, an electric car, you bet it does, as long as you're in the right places where electricity is generated differently, it can reduce your carbon footprint. Okay, and produce a lot less carbon dioxide than a similarly sized internal combustion engine powered car. The problem is when the batteries on it go, they are full of highly toxic chemicals. Okay, and so you have to pick your poison. There's poison either way. Okay, you just have to pick which one it is. Right. The other thing you have to know about an electric car is if you're buying it for the right reason, which is you want to reduce your carbon footprint, you have to look at where you get your electricity from. Okay, buying an electric car and using it in Alberta may reduce your carbon footprint a little bit, but in the end, most of our electricity comes from burning fossil fuels, and all you've done is, you know, kick the can down the road. Instead of you directly burning it, somebody else is burning it. Okay, it takes just as much energy to get to work, whether you use an electric car or a gasoline-powered car. Okay, and if your electricity is coming from burning fossil fuels, you know, sure, an electric car is more efficient. You can still reduce your carbon footprint a little bit, but not as much as a lot of people think they're doing. And I mean, it's great if they want to make that decision and try and be environmentally responsible, good on them. But unless your power is coming from something that doesn't produce greenhouse gases itself, you're not really helping the environment a whole lot. Okay? I think the biggest benefit of having is electric cars. I could go downtown and plug it in, and I don't have to pay for it. Okay? It's like getting gas for free. Seems wrong somehow, but okay. Okay? I can't just go, hey, well, I want to pull up in front of town hall and there should be a gas pump there for me, but there isn't. There's a plug-in, but I don't know. That's not, I guess that's above my pay grade. All right, so looking at this picture here, okay, what we have going on in this picture is something called the Inuit blanket toss. Okay, it's now mostly ceremonial, but way back it had a very practical purpose. It was used by the Inuit to help them hunt caribou. Where the Inuit live in the tundra, there's no really large geographical features, no big hills or river valleys or mountains or even trees to climb, okay, where they could see further than the horizon. Okay, it's basically like being in Saskatchewan. You know, like it's really flat. You can watch your dog run away for a week. Okay, you can see from one side of the province to the other. I won't run out. I've got lots of flat Saskatchewan jokes. In the tundra, okay, you have basically an Arctic prairie. That's what it is. And so it's very difficult to sneak up on your prey when there's nothing around to hide you. So what they would do is they would put a small member of their group on the blanket, and the rest of them would toss them up in the air. Okay? Well, when you get up in the air, you can see further. You can see a little bit over the horizon. It allowed them to kind of see where the prey was and kind of surround them, okay? And then they were more successful at hunting them, so it had that purpose. Now, in order to do this, it involves several energy conversions. Okay? What's the initial source of energy for this person who's going to be up in the air? Chemical energy, in the form of the food the people moving the blanket have consumed. Okay? As they pull on the blanket, they're converting that chemical energy in their cells into mechanical energy and changing the shape of their muscles, okay? And that mechanical energy is pulling up on the blanket. Now, the blanket is doing work on the person who's on it. Okay? It is changing or transferring to them mechanical energy and making them go really fast. Okay? Now, once they leave the blanket, they have a lot of kinetic energy, energy of movement. Okay? As they move upwards, what happens to that kinetic energy?
Decreasing.
It decreases. Does their mechanical, their total energy decrease? Actually, it doesn't. If this was the perfect physical world, okay, there wasn't any energy being lost. Okay? But their kinetic energy actually is getting converted into potential energy. The higher you go, the more potential energy, gravitational potential energy you have. Okay? So their kinetic gets converted into potential, and at the top of their flight, they can see a little bit further, and then that potential turns back into kinetic, and they have to hope that everybody holding onto the blanket is on the ball, because now those people holding the blanket need to take that kinetic energy away. They need to slow them down by pulling on the blanket and slowing them down before they crash into the ground. Okay, so there's a bunch of energy conversions going on in something as simple as tossing somebody up in the air. All right, so big idea here for energy. Okay? The idea of energy was actually very elusive for early scientists, and it's because energy is not matter. Okay? It's not something you can hold in your hand, right? It's not something that you can measure with a scale, okay, or something like that. It wasn't material. And that really gave people trouble because it was hard to explain it, it was hard to quantify it, it was hard to show how it moved or was, used to do things because there wasn't anything that they could physically see go from one place to another. Okay? So they started coming up with all these ideas for energy that kind of didn't make sense. Like it was this invisible fluid. That's the go-to for like early science. It's invisible and it's fluid, and it can flow. Everything was an invisible fluid if they couldn't explain it. Okay, and so it could flow from one thing to another because they understood that there was something that was going from a high energy object to a low energy object. So if you put a glass of really hot water right beside or in contact with a glass of really cold water, eventually the two would become same temperature, right? And they understood that the energy was flowing from the hot one to the cold one because the cold one got warmer and the hot one got cooler, okay? And so they understood that there was this flow of something, but when they measured the two cups, it wasn't like there was a change in the amount of anything. Like they still had the same mass they had when they were cold and hot. They were now both warm, but they had the same mass. Energy didn't have mass because energy wasn't matter. So it was really hard for them to explain it and kind of quantify it. Okay, so the big thing here is the definition of energy, okay? The ability to do work, okay? That's really important. That's something that's going to come up over and over again, okay? Now, instead of the ability to do work, what we typically envision is examples of it, Okay, sun melting snow in the spring. Okay, person who's run a marathon is tired. Okay, stuff like that. Okay, we only see the evidence of energy when something is done. Okay, if I look at a tank of gasoline, I can't really see that that has a lot of energy in it. Does it? Sure does. Okay, if it were to start on fire, it would get really, really hot. Okay, or that tank of gasoline has enough energy in it to move a vehicle hundreds, maybe even thousands of kilometers, depending on how efficient the vehicle is or how much fuel there is. Okay, but I can't just see that by looking at it. Okay, energy is difficult to quantify in that way. All right, so by the 1850s, scientists were convinced, okay, of the existence of the scientific concept of energy, okay, but it was still difficult to describe because it involved an abstract idea, not a material object. Okay. There was evidence from experiments that supported the theory that heat was a form of energy and that it could be converted into other forms following certain principles, okay, and that's what we do with the internal combustion engine. Okay? When you burn fuel in your vehicle, okay, when it ignites, it gets hot, obviously, okay, and hot gases take up more space than cold gases. So when you detonate, it's really an explosion. When you explode the fuel, okay, the hot gases exert pressure on the inside of the cylinder, which moves the piston downwards. Okay, that's the work phase of an internal combustion engine. When the expanding gases push the piston down, that's when work gets done. Okay, now there's lots of phases to that. There's cycles that allow the intake of fuel, the exhaust of burnt fuel, and all of that kind of stuff. Okay, but they know that, yeah, that's kind of what goes on. Okay, so with those scientific breakthroughs, scientists realized that other physical phenomena in science might be explained in terms of energy and that other forms of energy might exist. All right, so first form, chemical energy, because it's the one we use the most. Okay, early man discovers fire. Okay, that was chemical energy, right? So from experiments by the alchemists, we remember them from Unit 1. Okay, it was known that there were hidden secrets, okay, in chemical reactions. That is, some chemical reactions would get hot. Okay, some of them got hotter than others. Okay, this was what kind of led to the development of fuel. Okay, we know wood can catch on fire, and when it catches on fire, it gets hot. But if I burn a similar amount of coal, I get more heat. What's the better fuel, wood or coal? Coal's got more energy in it. Okay, if I burn gasoline, it also gets very hot. Okay, but it's more transportable than fuel, or than coal. Sorry. Okay, so we're looking at stuff like that, and the development of fuel led to, okay, here's stuff that's really concentrated, here's stuff that gets really, really hot. This can be used as a fuel better than this stuff can. Okay, so while they tried to make gold by mixing the four known elements, earth, air, fire, and water, the alchemists began to discover mixing certain chemicals could produce surprising results, like inventing gunpowder. I'm sure gunpowder was invented several times. Somebody just had to live long enough to tell everyone about it. Okay. So for the science of chemistry began, we talked about Antoine Lavoisier. Okay, he was one of the people responsible for this scientific method. Okay, he realized that when equal amounts of different substances were burned, the chemical reactions produced different amounts of heat. Okay, and with that discovery, chemists and physicists shared a common interest in heat. Right. So what's chemical energy? Chemical energy is a form of potential energy, because it actually has to be converted into something else. Chemical energy by itself can't do it. It has the potential to, but it can't by itself. Okay? A tank of gasoline is completely useless to me until I start it on fire. Okay? Then it becomes useful, because then its chemical energy is converted into heat. Now, where does that chemical energy come from? It comes from breaking the bonds in chemicals. Okay? So if I have, let's say I start up my barbecue, right? My barbecue burns propane. Okay? Propane is C3H8. So the propane molecule looks like this. When I react it with oxygen, okay, that reaction causes all of these chemical bonds between the carbon molecule, or between the carbon atoms and the hydrogen atoms, to break. Every time one of them breaks, energy is released. Okay? And so when I have this combustion reaction go on, I end up with carbon dioxide, water, and heat. Okay? The longer the molecule that I burn, the more energy it can release. Okay? So octane, okay, would be C8H18. Okay, it'd be a bigger molecule. That's the stuff that's in gasoline. Okay? Paraffin, which is candle wax, okay, is like C22H46 or something like that. Okay? It's a very long carbon chain molecule. It actually releases a lot of heat. That's why most emergency kits contain a candle. Okay? You can heat up a whole, like the inside of a car. If your car goes in the ditch and you can't run it anymore, you can just burn a candle inside the car and it'll be warm enough to keep you warm in there. It releases a lot of energy. Okay? It's just not practical as a fuel for cars because it's solid. It's difficult to get it to run into the engine. Okay? Liquids are easier. All right. So the food you eat is also a form of chemical energy. Your body breaks it down, right? Your lysosomes break it down into other forms, and your mitochondria can then carry out cellular respiration, which burns the glucose, okay, and releases it. All right, next kind of energy, electrical energy and magnetism. Okay, so what's electricity?
Electrons running through current.
Right, it's a current of electrons. Electrons flowing through something that can conduct them. Okay, electrons are tiny, but they move very fast. Okay, and we can use their kinetic energy, the energy of these moving charges, to power things. That's how an electric motor, okay, or anything powered by electricity works. As the electrons are flowing through, they are slowed down by something, okay, and when they're slowed down, they transfer their energy to whatever it is you have them hooked up to. A blender, a hair dryer, a heater, okay, whatever, okay, you're slowing them down and releasing the energy that they have, the kinetic energy that they have. All right, so electrical energy is the work done by moving charges, okay? Are these the kind of things that could show up on a quiz or a multiple choice question for this unit? Yes, okay. Now, the first person to kind of discover this, okay, or to be able to harness it, was an Italian scientist named Alessandro Volta. Okay, he's pretty important in so much as the units, okay, for electrical charge, volts, okay, are named after him. Okay. He developed the first battery. Okay, that picture there is the Volta pile. Okay, it is a pile of metal plates, okay, stacked together, and it is essentially the great-great-great-grandfather of the AA battery. Okay, today we use dry cells. Okay, that's what a AA or a AAA is, a dry cell. Okay, and it's simply layers of different chemicals. Okay, they have different amounts of potential difference between them. Okay, as soon as they are connected, the potential difference is it tries to equalize itself. And when it tries to equalize itself, the electrons flow from the negative pole to the positive pole.
Which chemicals were used back? Like,
You know what? I don't remember what metals were in there. I don't think it says in here either. Copper and silver, different materials such as copper and silver. So they would have a potential difference between them. Okay, and electricity, electrons will want to flow. Okay. All right. Now, of course, this thing was not very practical. Not at least in a modern sense. It was big and heavy and expensive because it contained copper and silver. Okay, so it, but it worked. It generated a small electric current, okay, and demonstrated that you can convert chemical energy into electricity in a portable way. Okay, now I wouldn't want to carry this thing around, but okay, it was portable for the time. Now, obviously, we have very much miniaturized versions of this that can generate a lot of electricity and be recharged.
how big was it?
I think this was like the size of a lantern. So, yeah, pretty big. Carrying it around would have not been practical. Okay? You're not just plugging a USB into that. I'm not charging the phone. Okay? It's not like the power packs that we carry around. Now, are batteries heavy? Yeah, they can be. I mean, you think about how big they are. Even a AA or a AAA battery is fairly dense. It's fairly heavy. Lithium-ion batteries, same thing. They're pretty heavy. They're pretty dense. Okay. If you have one of those little portable power packs, they weigh a lot. Okay, for the size. All right, so Alessandro Volta, okay, showed that you could convert chemical energy into electricity. That was his kind of big contribution in developing the first battery. Okay, now, these two people, Oersted and Faraday, are really important in terms of, in terms of their contributions as well, but their contributions had to do with the relationship between electricity and magnetism. Okay? These two things can be readily converted into each other. Okay? It's how wireless charging works. Right? So how many people have a wireless charger for the phone? Okay? So wireless charging, how it works is you have an electric current, okay, that goes into essentially a magnet, and the magnet makes a rotating or alternating magnetic field. Okay? And as that field alternates back and forth, it imparts a charge or induces a charge into the battery of your phone. Okay? Now you have to have a phone that's capable of wireless charging. Your battery has to be designed the right way for it to accept that. Okay? You couldn't take like an old iPhone, or something like that and throw it on a wireless charger. That would be unsafe. Okay? But it does work if you have one that's designed properly, okay, where that induced magnetic field can actually result in moving charges. Okay? Because a magnetic field can push electrons. It can get them moving. And once electrons are moving, you have a current. And a current is capable of imparting energy from those moving electrons. Okay? So a wireless charger essentially uses a magnetic field, an alternating magnetic field, to accelerate electrons, and then they have kinetic energy that can be added to your lithium-ion battery in your phone. Okay? But it was Oersted who initially discovered this relationship. Okay? He was actually just demonstrating something, and he had a compass and he had a current-carrying wire. Okay? And he had no intent, this was completely by accident, but he started the electricity flowing, and the compass just happened to be near the wire. Okay? And instead of pointing north, the compass pointed parallel to the wire, in the direction the current was flowing. And he looked at him, that's weird. I'm pretty sure that way's north. Why is my compass pointing this way? And then we flipped off the power, the compass went back to pointing north. Flicked the power back on, the compass immediately pointed parallel to the electric field, okay, to the electric current. So he discovered that an electric current produces a magnetic field. That is, electricity can produce magnetic effects, okay, and vice versa. Magnets can produce electric fields and impart current. Okay? So it was an important relationship to discover. Okay? And Faraday discovered that, yeah, the opposite can be used to generate an electric current. So if he pushed a bar magnet through a coil of wire, he would get a current that would flow. Okay? Because the magnetic field around the bar magnet would push the electrons through the wire. Okay? As long as the magnet was moving, the electrons would move. Okay? And that's how some of the first generators were made. Okay? They produced alternating current because the magnet would go in and out of a coil of wire, okay? Causing the direction of current to alternate. Alternating current, AC. Okay? All right. Okay, so that's converting electricity to magnetism and vice versa. Okay? And then it was discovered that you can actually turn heat directly into electricity. It's not very efficient. Okay, but it works. You can actually turn thermal energy directly into electricity by using a thermocouple. Right? We use thermocouples in circuit breakers. Okay? If too much electricity flows through the wire, it can obviously get hot. That's what can start fires. We don't want that. So there's actually a thermocouple, okay? And as it gets hot, it generates enough current to trip the circuit. Okay? And that is open the circuit. And then when there's no electricity flowing, the circuit cools. Right? So we can use a thermocouple for that. We also use them in the brakes of hybrid and electric vehicles. Not all, but some. Okay? They put a thermocouple in the brakes so that when you apply the brakes and the brakes get hot, the heat is converted into electricity, which is then used to recycle and charge the battery. Okay? It's not huge, but it increases the efficiency of the electric vehicle. Okay? Essentially taking its kinetic energy that would otherwise be wasted as heat and turning it back into electricity. All right. So it was Thomas Seebeck, who was an Estonian scientist, okay, who discovered this. And what he did is he took an iron bar and he welded a piece of copper or screwed a piece of copper onto it, and then he put a compass needle in between. Okay? And because heat flows through iron and copper differently, okay, as he started to heat the iron, the particles in the iron start to move faster according to the particle theory. Okay, they would move faster, and that heat was slowly transferred along the iron. Okay, when it got to the copper, the heat was able to transfer or conduct through the copper much more easily. Okay, and what he ended up getting, okay, was essentially an electric current flowing through these two conductors, and that caused the compass needle to go from pointing north to parallel to the metals, indicating a current was being produced by the heat. Okay, again, it's not a lot. It's not something we would use to generate large amounts of electricity because it's very inefficient. Okay, but it is possible. All right, so that was the first thermal-electric converter, or thermocouple. So that was CVEC. Okay, now, nuclear and solar energy. Okay. Nuclear energy comes from where? Don't say nuclear power plants, that's not the answer I'm looking for. From the nucleus. It is energy stored in the nucleus of an atom. Okay? Anytime we change the nucleus of an atom, the energy involved in holding the nucleus together is released. Okay? So typically what we use is fission, nuclear fission. Fission is the splitting of the atom. Okay? So when you hit a large atom with a smaller particle and it breaks open, okay, or breaks apart, the energy that was previously used to hold it together is released. Okay? It's released as heat, and there's fairly large amounts of that involved for the size of the stuff we're talking about. And so if you have, a large concentration of uranium or something that's fissionable, okay, it can release a lot of energy when the atoms break. The other type of nuclear energy is fusion. Okay? Fusion involves when you force two atoms together. All right? Typically what we would see as a typical fusion reaction would be a hydrogen-hydrogen fusion. Okay? That is, two or three hydrogen atoms are pushed together to create one helium atom and some free neutrons and a lot of heat.
So technically any atom could be used for nuclear energy.
Technically, everything, well, it depends. For fission, you could never use a hydrogen atom because there's nothing to break. The smaller it gets, the less energy is used to hold it together, the less effective it becomes. Right? The big molecules, they kind of break apart on their own. They're already unstable, and they release a lot more energy. Plus, they're a bigger target. Okay? I would want to try and split helium atom. Okay? It's not a very big target. It's just not very effective at that. Does that make sense?
Yeah.
Okay? And similarly, it's very difficult to fuse large atoms. Okay? It's easier to fuse small atoms. It's easier to split big atoms. Okay? So that's typically how that works.
Isn't fusion what happens in the sun?
Exactly what I was getting to. Yes, fusion is what powers the sun. Hydrogen-hydrogen fusion is what powers the sun. Okay? Now, in order to make fusion occur, you have to have a lot of force. Okay? It takes a lot of force to push two atoms together and fuse them. That is, turn them into one larger atom. Okay? Now, the sun makes that happen because the sun is massive. Okay? To give you an idea here, this number here, the 5.98 times 10 to the 24 kilograms, that's the mass of the Earth. Okay? The number below it, 1.99 times 10 to the 30, okay, is several million times bigger. That's the mass of the sun. Okay? When you look at the mass of the solar system, the entire solar system, everything in it, 99% of it is the sun. Okay? The sun is huge. Okay? And it's made almost entirely of the lightest element there is, hydrogen. But there's so much of it that the sun's mass creates all this gravity that holds the planets in orbit. Okay? But all that gravity is also so strong that it literally crushes hydrogen atoms together to form helium atoms. Okay? So early on in the formation of our solar system, there was no sun. Okay? Just debris and dust and gas. Okay? And that gas started to coalesce, and the more gas that came together, the more gravity it could generate. The more mass you have, the more gravity you're capable of generating. Okay? That's why the Earth can hold the moon in orbit, and why the moon doesn't leave the Earth to go to the sun. Okay? The moon is very close to the Earth, and the Earth is pretty massive. Okay? If the moon was any further away, it might leave, because it might be more attracted to the sun then, because the sun is way more massive.
What do you mean by created heat? Like created heat?
What do I mean by creates
Yeah,
helium?
like hydrogen.
Okay, so if I take hydrogen atoms, okay, which are a proton and an electron, okay, if I take, I think it's 3 of those, and I force them together, crush them together, okay, what ends up happening is those protons merge, but one of them actually becomes like a free neutron that kind of just flies off. Okay, there's a lot of energy in that. There's also a lot of heat energy that's released when I combine those nuclei together. And then what I end up with is a helium atom. Okay, so a hydrogen atom, okay, 1 proton, 1 electron. Helium atom, 2 protons, 2 electrons. Okay, so you force them together. Yeah. It's just a matter of kind of overcoming their natural tendency, okay, which is to stay separate. Okay, but when you have that much gravity involved, there's enough force there to literally crush them together.
So the rule that you said in chemistry that like an atom can't be changed to another one, in this case in gravity, like this is the one exception, right?
What we said is in a chemical reaction, you can't change one atom into another. Okay, so you're talking about the atomic theory, okay? And we're saying that in a chemical reaction, atoms are not changed into other atoms. In a nuclear reaction, all bets are off. Yes, I can definitely change atoms into other atoms because I'm physically changing the nuclei. I'm not chemically changing the nuclei, that doesn't happen. But in a physical reaction, and that's what this is, I am changing the nuclei. Does that make more sense? All right, so that's what we've got going on the sun. Okay, we've got tons of this nuclear fusion going on. Okay, so much so that like we can't even fathom the amount of energy that is put out, okay, by the sun due to the number of fusion reactions always going on. Okay, so solar energy, like I said, results from the hydrogen nuclear fusion energy. Originally, scientists looked at the sun and they went, oh, that's bright, and then they realized that it looked like a big fire. And like, fire means burning fuel. And they assumed, incorrectly, that the sun was a big chemical fire. Okay? Because of course at that time they didn't understand the sun was millions of miles away in the vacuum of space and that a fire can't burn in the vacuum of space, not a chemical fire. Right? Then people started doing the math and they realized no matter what fuel the sun was made out of, it could never burn for as long and as hot as it's been burning for. Okay? If it was a chemical fire, it would have run out of fuel in 5,000 years. Okay? But because it's a nuclear fire, okay, it doesn't run out of fuel nearly as fast. And the sun will go through different phases, okay, in its life cycle, right? It'll eventually burn through its hydrogen fuel supply. Okay? And when that happens, it'll start fusing the helium together. And when it starts to do that, the sun is going to change drastically. Okay? It's going to swell, right? Because helium fusion is a much different reaction. Okay? The sun will swell into a red giant and it will engulf Earth. Okay? It'll get that big. And then, since it doesn't have sufficient mass, it'll kind of just run out of ability to fuse materials anymore. When it does that, it'll cool and it'll collapse. Okay? And it'll become like a little white dwarf. Okay? And that'll be kind of the end of our sun. Don't worry, it's not happening tomorrow. Okay? Still like 3-4 billion years away. Not going to be our problem. Okay? We can label that as not our problem.
So when the sun runs out of hydrogen and starts using helium,
Yeah.
does that mean we'll start making beryllium as a result?
And other heavy molecules, yes. Yeah. Okay, like the presence of all heavy atoms, okay, is from fusion within massive stars. Okay, our sun is not a massive star. Our star is kind of on the bottom end of average. Okay? It's actually kind of a smaller G-type star. It's very common, but also not very big. Okay? If you're looking at, like, there's blue stars. Okay? Blue stars are supermassive. Okay? If our sun was to be replaced by a blue star, the blue star would go like pretty much to Saturn. It'd be that big. Okay? It'd be huge, right? And because it has so much more mass, it burns way hotter. So it has no problem fusing helium, beryllium, even carbon. Okay? Like it can burn for a much longer time. But when it starts to burn those heavier fuels, it swells to a red supergiant, and then goes supernova. You have to have enough mass in order to make a supernova. Our star doesn't have that kind of mass, so it's not going to do that. It's just going to go out there and burn. Okay, So that's nuclear energy. Now, motion and energy. This is the mechanical energy stuff that we're going to deal most with in this unit. Okay, so when a group of English scientists watched a demonstration of Newton's cradle, you guys seen Newton's cradle? Okay, it just goes tick, 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 and balls go back and forth. Okay, they had no idea why the ball on the opposite side rose to nearly the same height as the first ball. In fact, nobody really understood this, and Newton got himself in a lot of trouble. Okay, the early church was not as open to ideas and science and explanation as our modern church. You're very lucky. Okay, Pope Francis actually is a chemist. You didn't know that. Okay, his original area of study was chemistry, so he's very open to the idea of religion and science being okay with each other. Okay, the early church not so much. So Newton builds this thing. He's like, look, isn't this cool? And like, you're a witch. How did you do that? That's not possible. We're going to have to set you on fire. Okay, or weigh you down and throw you in the lake, or whatever they did all those awful things to the people they thought were witches. Okay, so he got himself in a lot of trouble, so he had to kind of backpedal a little bit. He's like, well, actually, there's this living force, and I'm not a witch, it's not like that, but okay, there's this vis viva thing going on where I pull this ball over here, and when I do that, I give it a part of me, and then I let it go, and it can take that part of me and transfer it to the other ones. That doesn't make me a witch, because you could do it. And they're like, hell no. I'm not touching that. I'm not a witch. Right? So there's all this kind of fear around this simple thing that we laugh about it now, right? It's pretty simple, but people looked at that and they're like, that ain't right. No, that ain't right. You're a witch. Okay. So he got himself in a bit of trouble, but he was able to explain it, and that actually gave rise to the initial ideas of energy. There was this living force that could be imparted to things. Okay? We now know that process as work. Okay? We do work. Okay? When he lifted the first ball away, he gave it mechanical energy. He transferred mechanical energy to it. When he released it, that potential energy became kinetic energy. And when it hit the next ball, it did work on that ball and imparted energy. That energy was transferred through the balls to the one on the other side. And since there was nothing to stop that one on the other side, it flies up. Okay? It's just a transfer of mechanical energy that's going on there. Simple as that. Okay? All right. So, examples of mechanical energy, flowing water. Okay? There's a reason we build hydroelectric dams. Flowing water has energy. Right? We take its potential energy at the top of the dam, okay? We let it fall, and as it falls, it turns the turbines. Its potential turns into kinetic. Its kinetic energy does work by turning the turbine. The turbine generates electricity. Water comes out the bottom, okay, and flows away from the dam. All right? So it has kinetic energy. Okay? An object that's raised above the Earth's surface has the potential to do work, okay, because of its position, and thus has gravitational potential energy. Okay? I mean, if you see a piano sitting on the floor, it's not very scary. You see one hanging from a rope over your head, it's a little more intimidating, okay? And just naturally, we understand that has the potential to do work. It could change my shape in an undesirable way, or it to fall, okay? We just get it, it's there, okay? We can see and feel that it has this energy, okay? All right, so this idea of these two things, kinetic and potential energy, okay, combines to this. Okay? The sum of the energy of motion and position, so that is the sum of kinetic and potential energy, is mechanical energy. So you might want to add this somewhere. Okay? That mechanical energy equals the kinetic energy plus the potential energy. Okay, that is something we are going to use over and over again in the second half of this unit. Okay, questions there? Now, heat and energy is something that kind of people understood those two things went together, but they didn't understand always how they went together. Okay, so in 1750, a physician named Joseph Black observed that when a cold object is placed in a cup of hot water, it gets hotter. Mind-bending stuff, okay? Now, why does that happen? Because the hot water has energy. It has thermal energy, which we typically call heat, but thermal energy is technically more correct. Okay? It has thermal energy and it can transfer. Thermal energy always moves from the hotter object to the colder object. Okay? You cannot transfer coldness. Okay? People have this idea that you can transfer coldness. That's why you put ice cubes in a drink. You put ice cubes in the drink to make the drink colder. Okay? What people don't understand is the drink gets colder because the ice cubes are absorbing the heat energy from the drink. Okay? And because of the nature of water, it takes a lot of energy to melt water. Or sorry, to melt ice. Melt water. Okay? To melt the ice. But while ice is melting, its temperature doesn't change. It's just absorbing energy in order to change state. Okay? So the idea of they transfer coldness to the drink is wrong. There's actually the drink losing energy to the change of state of ice to water. Okay? All right. So Joseph Black came up with this idea that there's this flow of something. I don't know what, but there's a flow from the hot to the cold. I'm going to call it caloric fluid. This invisible fluid that magically makes my idea work. Okay? So he suggested that naturally flows from hot to cold things. Black mistakenly thought that a substance was being transferred. Okay? There can't be a substance or there'd be a change in mass. Okay? Being transferred to the water, or from the water to the spoon. However, his observation on the flow of heat became one of the principles of thermodynamics. In fact, it's the second law of thermodynamics. Energy always flows from hot to cold. Okay? That's the second law of thermodynamics. Okay, so here's the technical thing that we need to understand. Heat is not a form of energy. Heat is a transfer of thermal energy. Okay, so when I say, oh, I feel the heat coming off of that, okay, what I'm saying is I feel the transfer of thermal energy from that hotter thing to me. Okay, so I'm standing by a campfire, I feel heat because I feel the transfer of thermal energy, okay, from the campfire to me. But saying heat makes you sound less strange. Okay, because you go to a party or something and you're standing around the fire and you go, hey, I feel the transfer of thermal energy here. People are going to go, yeah, cut him off. He's had too much already. Okay, they're going to think he's strange. Okay, all right. So just remember that. Okay, that's an important definition for you to know. Heat is not a form of energy in and of itself. It is the transfer of a form of energy, that being thermal. Okay. In 1800, this American-born industrialist named Benjamin Thompson, who later changed his name to Count Rumford, don't ask me why, okay, became the Minister of War in Bavaria. The job of the Minister of War is to supervise the production of cannons, because at that time cannons were used for war. Okay? So he's supervising workers who are boring out these brass cylinders, okay, because cannons were made of brass, okay, and so they were boring out these cylinders made of brass with essentially a big drill, right? So it would look like an auger if you've ever used like a post hole auger, an ice auger, or something like that. Okay, they were turning these things by hand, okay, and essentially boring a hole in the cylinder to make it hollow, make it a cannon. Okay, now what he noticed was the workers at the start of the day would take a tea kettle and they would put it on top of this brass cylinder, and then they would start turning the drill. Okay? And after a while, the tea kettle would boil. And he's like, well, that's kind of cool, but it takes heat to boil water. Where's the heat coming from? Okay? And what he eventually discovered was he traced kind of the line of energy transfers that led to heat going to the tea kettle. Obviously, when you push two materials past each other, there's what? Friction. Does friction make heat? Okay, so what he figured was, all right, the turning drill is obviously going to generate heat. If you've ever drilled anything, especially metal, okay, you know that the bit and the metal get really hot. Okay, so there's a lot of friction there. Okay, and what these people were doing was they were using their own chemical energy from their food, converting it into mechanical energy by their muscles, and turning this drill. Okay, turning the drill through the metal made the metal get hot enough that after a while they could make tea. Okay, the invention of the coffee break. If you worked hard enough for a while, you made enough heat that you could boil water and make tea, and then you could have tea, and then you have to get back to work again. Right? Okay, so he noticed huge amounts of heat were being generated in the bored metal. In fact, you could boil a kettle of water on the cannon. Now, workplace health and safety. Okay, during said coffee break, do not lean on the cannon. Okay, caution, hot. Yeah, you have to watch out for that. All right, now Rumford suggested that heat could be manufactured by the motion of the workers. That's where it came from. He was the first person to realize that mechanical energy and heat were related and could be converted into one another. Okay, much easier to convert mechanical energy into heat than vice versa. Okay, but he discovered that those two could cause each other. Okay, a little while later, a guy named Thomas Young linked mechanical energy to this idea of kinetic and potential. Okay, that Leibniz had come up with earlier. Okay, and that led to our current definition of energy, which is the capacity to do work. Okay, the workers had energy, they were able to turn the drill. Okay, that's a form of mechanical energy, and that mechanical energy was turned into heat. Okay. All right, questions on that? Okay, so heat and mechanical energy go together. All right, then a guy named Joule comes along. How important is Joule? Pretty important, given that the units for work and energy are named after him. Okay, you can always tell how important somebody is if they have physics units named after them. Okay, like newtons, for example. Okay, units for force, newtons. Okay, Newton is pretty important. Okay, so a guy named Sadi Carnot, who was a French engineer, was performing these experiments, and he was attempting to transform heat into mechanical energy, which now, of course, is what we use in the internal combustion engine. Okay, he discovered that transformation of heat into mechanical energy could only occur when thermal energy flowed from hot to cold. Okay, it had to be able to flow. He had to get it moving in order to harness its energy. Okay, so he discovered that in this process, some heat was always lost. And from those experiments, he was able to determine the laws of heat efficiency in heat engines. He actually built a heat engine, which is an engine that simply uses the flow of heat, okay, in order to make something move. A jet engine is a heat engine. Okay? On one side of the fans, if you've ever seen what a jet engine looks like, it's a series of fan blades. Okay? On one side is where the jet fuel is burned. The other side is cold air. Okay? When you start burning that fuel, the hot air quickly tries to move to the cold air, right? By the second law of thermodynamics. As it moves through, what does it do to the fan blades? It turns them, creating thrust. Okay? That's how a jet engine works. Okay? In order to make a jet engine work, you have to burn really, really hot fuel. Okay? The temperature difference needs to be huge in order to get those fan blades moving very, very fast. Okay? All right, so here's what Joule discovered. Okay? Joule ran these experiments that proved, okay, that potential energy was a form of mechanical energy. Okay? His first experiment was the falling block experiment. Okay? And he said, if I move, he had these two blocks, okay, two wooden blocks. And in this block, the stationary block, he had a thermometer. Right? The other block was just on on strings, and he would pull it up and away from the stationary block. When he pulls it up and away, what has he done? Right, he's done work and given it potential energy. Okay? Now people are like, so how can you prove that it has energy? And you're like, well, it'll fall. Everything falls. That's stupid. Okay? That was people's argument. That's stupid. Everything falls. That doesn't mean it has energy. And he's like, well, would you want it to fall on you? No. But he needed to prove somehow that this stuff had energy. He said, watch. I'll convert the energy that I've just given that block into heat or into thermal energy. And they're like, no, you won't. So, okay, fine. So he pulls the block up and away and lets it go. And it smashes into the stationary block. What happens to the thermometer? It goes up. Okay? Super easy experiment. You can try it at home. Take a hammer, piece of wood, okay? Just hit the wood a couple of times, a few times with the hammer, put your thumb where you were hitting. Stop hitting. Put your thumb where you were hitting. Okay? What are you going to notice? It's hot, yeah, okay. I mean, you're constantly converting mechanical energy when you hit that piece of wood, okay? That mechanical energy is getting converted into heat and sound and all that other stuff, okay? That's all he did there to prove that, okay? And then he proved it again with this experiment, which was a bit more complex, but actually this one he was able to, because he knew the masses that he had, he was actually able to calculate how much energy would be there and see it all transferred to the air inside this jar. So he had a thermometer inside this jar and these blades, like fan blades essentially in there. And as the blocks fell, this thing would rotate. And as the fan blades would move through the air, they'd get hotter. Okay? So he proved this is a form of energy because I can convert it into a form of energy you're more familiar with. Okay? Potential energy is a real thing. Here's why. Okay. I would like you guys to answer the circled questions. Okay, this is in the workbook, or is it in the notes packages? Okay, so questions you're working on are on page 6 of the notes package for Unit 3. Okay, and I am going to want you to do question number 2, 3, 4, 6, 9, 10, 12, 13, and 14. Okay? None of them are terribly difficult questions. Okay? You don't need to have like a novel for an answer for any of them. Okay? Just want you to write down some stuff about each one. Okay? Maybe we'll even have time to go through that, but we might have to go through it at the start of tomorrow's class. Okay? So rest of class, I want you working on those questions there, please.